Hello friends, I welcome you in lecture number 22 on first order ODEs. In this lecture also we will do some more miscellaneous problems. So let's start with this problem number 1. Solve dy by dx plus x over 1 minus x square y equal to x times square root of y. So as we know, there are mainly three types of differential equations of first order: separable, exact and linear. And if your differential equation is not of any of these three types, then either it can be reducible to any of these three types. So if your differential equation is not separable or not exact or not linear, then you can check whether it is possible to convert it into separable or exact or linear. So first we check whether this is separable or not. So if you observe this equation here, if we try to separate the variables, then first we have to write dy by dx equal to x times square root of y minus x over 1 minus x square times y. So now because of this negative sign, we are not able to separate the variables x and y. That means we are not able to write our differential equation in this form: fx into dx equal to gy into dy. So this equation is not separable. Now we can check for exactness. So I am not doing for exactness, but you can check by writing your differential equation in this form. You will find that your differential equation is not exact. So for that you have to first write this equation in this form and then check the exactness condition, and you will find that this equation is not exact. Third type is linear differential equation. So if we recall, a first order differential equation which can be written in this form is called linear differential equation with y as dependent variable. So this equation, in this equation, if you compare, left hand side is in this form, but on the right hand side we have mixture of x and y. So right hand side is not function of x only, so this is not linear differential equation if we consider y as dependent variable. And similarly we can check that it is not possible to write our differential equation in this form, that is linear differential equation with x as dependent variable. If you find out dx by dy, then also it will not be possible to write this equation in this form, because we can see here power of x is 2, and linear differential equation with x as dependent variable must have power of x 1. So this is not separable, exact or linear. So now we can try to check that whether it is possible to convert this equation into separable or exact or linear differential equation. So if you recall, we have discussed this Bernoulli's differential equation: dy by dx plus px into y equal to gx into some power of y. So if our differential equation is in this form, it is known as Bernoulli's differential equation. So you can observe that given differential equation is in this form with px equal to x over 1 minus x square, gx equal to x and a equal to 1 by 2. So we can convert this Bernoulli's equation into linear differential equation by changing the dependent variable y. So given equation is Bernoulli's differential equation, and now we try to convert it into linear differential equation. And linear differential equation is in this form. So this equation is not linear because right hand side is not function of x only. So first we must express right hand side as a function of x only. So this is creating problem. So first we have to divide this differential equation by square root of y. So first step is we divide this equation by square root of y. Dividing given ordinary differential equation by square root of y, we get 1 over square root of y, that we can rewrite as y raised to minus 1 by 2 dy by dx plus x over 1 minus x square times y over square root of y, that is going to be square root of y, and that we can rewrite as y raised to 1 by 2 equal to x. Square root of y will cancel out here. Now again, this is not a linear differential equation. Again we write down the standard form of linear differential equation. So now right hand side is function of x only, but this y must have first degree. Here y is having 1/2 degree, or degree of y is not 1. So this suggests us to change the variable y to new variable by the substitution y raised to 1 by 2 equal to say v, because here power of y must be 1. So now we are trying to convert our differential equation into linear differential equation in the new dependent variable v. So now we will try to convert this differential equation in this form by the transformation y raised to 1/2 equal to v, where v is also a function of y, or v is new dependent variable. So now we give this number 1 and we consider the substitution y raised to 1/2 equal to v. We give this number 2 and we differentiate this 2 with respect to x on both sides. We have now y is a function of x and we are differentiating y with respect to x. So we apply chain rule. First we differentiate y raised to 1/2 with respect to y, and in the product we will write dy by dx. Derivative of y raised to 1/2 is 1/2 times y raised to 1/2 minus 1, that is minus 1/2 times dy by dx equal to derivative of v with respect to x. Therefore y raised to minus 1/2 dy by dx becomes 2 times dv by dx, and we give this number 3. So now we substitute these values in equation 1. Y raised to minus 1/2 dy by dx is 2 times dv by dx. So in the next step, using 2 and 3 in 1. In 1, first term is y raised to minus 1/2 dy by dx, that we replace by 2 times dv by dx. Second term is x over 1 minus x square into y raised to 1 by 2, that we replace by v, plus x over 1 minus x square times v equal to right hand side is x. Let me check. Yes, it is x. Now to convert this into standard form of linear differential equation, we must have this coefficient 1. So we multiply by 1/2, or we divide the whole equation by 1/2. We divide the whole equation by 2, or we multiply whole equation by 1/2, and we have this v equal to x over 2. So this is now linear in new dependent variable v and x, which is linear in v and x. So this is now easy to solve. First we compare this with standard form of linear differential equation with v as dependent variable, comparing with dv by dx plus px times v equal to rx. We can see coefficient of v is px. So we have px equal to 1 by 2 times x over 1 minus x square, and right hand side is rx, which is x over 2. Next step is to find out integrating factor. Integrating factor is given by e to the power integral of px with respect to x. So here px is, we can take 1/2 outside, x over 1 minus x square dx. Now to find out integral, we can set the derivative of 1 minus x square in the numerator. Derivative of 1 minus x square is minus 2x, so we can multiply and divide by minus 2x. So if we divide by minus 2, we will have minus 1 by 4 here. Okay, here there is x only, and derivative of 1 minus x square is minus 2x, so we multiply and divide by minus 2. So here this constant will be minus 1 by 4. Now integral is logarithm of denominator, which is 1 minus x square, and this we can rewrite as ln 1 minus x square to the power minus 1 by 4, and this is nothing but 1 minus x square to the power minus 1 by 4. So this is the integrating factor. Integrating factor is 1 minus x square to the power minus 1 by 4. And we have ready-made formula for the general solution of linear differential equation. So therefore the general solution is v times integrating factor equal to right hand side, which we have denoted by rx, times integrating factor, integral is with respect to x, plus c. Therefore v times integrating factor is 1 minus x square raised to minus 1 by 4, and let me check what is right hand side. It is x by 2. X by 2 times 1 minus x square to the power minus 1 by 4 dx plus c. Integrating factor was 1 minus x square to the power minus 1 by 4. Now we have to set, here also we have to set the formula for integral, and we can try that formula. Integral of function of nth power of fx times its derivative is equal to n plus 1th power of fx over n plus 1 if n is different from minus 1. So we can set this formula here. So we can observe that derivative of 1 minus x square is minus 2x. So here also we can set that derivative 1 minus x square raised to minus 1 by 4, and I multiply with minus 2. So I have to divide by minus 2 dx plus c, and here power is minus 1 by 4. So we have rewritten x as minus 2x divided by minus 2, and therefore, and what is our v? V was y raised to 1/2. So we put value of v also, y raised to 1/2 1 minus x square raised to minus 1 by 4. Now here this constant will be outside integral, and it will multiply with 1/2, and we will have minus 1 by 4, and integral of this is going to be 1 minus x square raised to minus 1 by 4 plus 1 over minus 1 by 4 plus 1. Therefore left hand side is y raised to minus 1/2 1 minus x square raised to minus 1 by 4 equal to minus 1 by 4 constant, integral of 1 minus x square raised to minus 1 by 4 is minus 1 by 4 plus 1 over minus 1 by 4 plus 1 plus c. Integral of this 1 minus x square raised to minus 1 by 4 times derivative of 1 minus x square is 1 minus x square raised to minus 1 by 4 plus 1 over minus 1 by 4 plus 1, and constant is 1 half into minus 1 half, that is minus 1 by 4, and this we can rewrite as denominator is going to be 1 minus 1 by 4, that is 3 by 4, and here we have 1 minus x square raised to 3 by 4 plus c, and left hand side is y raised to 1 half 1 minus x square raised to minus 1 by 4. Here 1 by 4 will cancel out, therefore y raised to 1 half 1 minus x square raised to minus 1 by 4 equal to 1 minus x square raised to 3 by 4 over 3 plus c. So this is the general solution of given differential equation, and c is arbitrary constant. So given differential equation was Bernoulli's differential equation, which was non-linear, and we have converted it into linear differential equation. We consider one more problem. Solve y dash equal to 10y over x minus 1. This we can rewrite as dy by dx equal to 10y over x minus 1. So first we can think whether it is possible to separate the variables or not. So here we can see this 10y is function of y, x minus 1 is function of x, and they are not in the combination. So we can set function of y with dy and function of x with dx. So I take 10y on the left hand side, and I will have 1 over 10y dy equal to 1 over x minus 1. I take dx on the right hand side. So this equation is easily separable. This we can rewrite as cot y dy equal to 1 over x minus 1 dx. So this is separable. And if our equation is separable, we find out its general solution by integrating both these sides. We integrate left hand side with respect to y and right hand side with respect to x. Integral of cot y is ln sin y equal to integral of 1 over x minus 1 is ln x minus 1, and we can set arbitrary constant as ln c because we are having logarithmic function in each of the remaining terms. Therefore ln sin y equal to, using the property of logarithm, this we can rewrite as ln x minus 1 times c. Therefore sin y equal to x minus 1 times c, which is general solution, and where c is arbitrary constant. So some equations are very easy to solve if they are separable. We just have to integrate by separating the variables. We move towards the next problem now. Solve the differential equation 3 times e raised to x tan y dx plus 1 plus e raised to x sec square y dy equal to 0. So from the observation we can see it is not possible to separate the variables, or we can try. Suppose we consider 3 times e raised to x tan y dx equal to, we take this on the right hand side, 1 plus e raised to x sec square y dy, and here I have to put negative sign. Now what we can check is whether it is possible to separate the variables. So we consider terms with x on this side. So we have e raised to x over 1 plus e raised to x dx equal to sec square y over 3 times tan y. We take 3 tan y on right hand side, we take 1 plus e raised to x and dy. Okay, fine. So this is separable. So from the very first observation I found that it might not be separable, but if I try to check, then I find that it is separable. So this equation is separable, and let me write systematically. Given ordinary differential equation is 3 times e raised to x tan y dx. We consider this quantity on right hand side minus 1 plus e raised to x sec square y dy. Therefore e raised to x over 1 plus e raised to x, if we wish we can keep 3 here, dx equal to minus sec square y over tan y dy. We have taken this 1 plus e raised to x on left hand side, and from this we have taken tan y on right hand side, and we find that this is separable. So all we have to do is integrate both the sides. Integrating, we obtain 3 times, let me write the integral sign, e raised to x over 1 plus e raised to x dx equal to minus, here we have sec square y over tan y dy plus c. So we can see derivative of 1 plus e raised to x is e raised to x, which is in the numerator. Similarly, derivative of tan y is sec square y, which is also in the numerator. So we can use this formula. If we have fx in the denominator and its derivative is in the numerator, then this is equal to logarithm of fx. So using this formula, we obtain 3 times logarithm of 1 plus e raised to x equal to minus logarithm of tan y plus, we are having logarithm in each term, so we can set arbitrary constant as log c, and we are using this formula. Therefore logarithm of 1 plus e raised to x to the power 3, and this we can rewrite as logarithm of c over tan y using the properties of logarithm. And because logarithmic function is one function, we have 1 plus e raised to x to the power 3 equal to c over tan y. So this is the general solution. So this equation also is separable. So the first observation we have to keep is check whether it is possible to separate the variables, and if it is not separable, then try for linear or exact. Next problem, solve the differential equation x plus y minus 2 dx plus x minus y plus 4 dy equal to 0. So this is obviously not separable because we have x and y in the addition, and this is obviously non-linear because it is not possible to write this equation either in this form dy by dx plus px into y equal to rx, or we can check by finding dy by dx. So if we find out dy by dx, first we will take this term on right hand side, and then we will have dy by dx equal to x plus y minus 2 over x minus y plus 4. So here it is not possible to write this equation in this form, dy by dx plus px into y equal to rx, or dx by dy plus py into x equal to r of y. So this equation is not linear, it is not separable as well as not linear. So now we can check for exactness. So for exactness we have to differentiate coefficient of dx with respect to y. So derivative of this function with respect to y is 0 plus 1 minus 0, that is 1, and we have to differentiate coefficient of dy with respect to x, and the derivative of this function with respect to x is also 1. So this equation is exact. So we can solve it by the method of solving exact differential equation. So first we comparing given differential equation with m dx plus n dy equal to 0. We have capital M equal to x plus y minus 2 and capital N equal to x minus y plus 4. Therefore partial derivative of m with respect to y is 0 plus 1 minus 0, that is 1, and partial derivative of n with respect to x is derivative of x is 1, derivative of y plus 4 is 0. So both the partial derivatives are equal, therefore del m by del y equal to del n by del x. Therefore given differential equation is exact. Therefore we write the formula for general solution of exact differential equation. Therefore general solution is integral of m with respect to x, consider y as constant, plus consider those terms of n which do not contain x. Terms of n not containing x, integrate those terms with respect to y equal to c. Therefore first we write down what is capital M. It is x plus y minus 2. So we will integrate x plus y minus 2 considering y as constant. Now we concentrate which terms of n are free from x. So first term contains x and these two terms are free from x. So terms free from x are minus y plus 4. So here we write minus y plus 4 and integrate with respect to y equal to c. Now here we integrate with respect to x. Integral of x is x square by 2. Y is constant. Integral of dx is x minus 2. Integral of dx is x. Here integral of minus y is minus y square by 2. Integral of 4 is 4y equal to c. And we can take 2 LCM. We multiply whole equation by 2 and we have x square plus 2xy minus 4x minus y square plus 8y equal to 2c. We have taken 2 LCM, so these terms are multiplied with 2. This is also multiplied with 2. So this is the general solution. We can consider this 2c equal to some new constant. 2c is arbitrary constant that we can denote by c dash, where c dash equal to 2c is arbitrary constant. So this equation was exact, and we are able to solve it by the formula for general solution of exact differential equation. And this is the last problem of this lecture. Solve 2x cube plus 4y dx minus x dy equal to 0. So we can see here we have functions of x and y in the addition, so this is not separable. We can check for exactness. For that we differentiate coefficient of dx with respect to y. So derivative is 0 plus 4, which is 4, and we differentiate coefficient of dy with respect to x, and it is minus 1. So this is not exact and it is not separable also. So what we can check is linearity. So for that we rewrite this equation as 2x cube plus 4y dx equal to x dy. Then we find out dy by dx. So dy by dx is we divide this quantity by x and we take dx on right hand side. So we have 2x cube plus 4y over x. Therefore dy by dx is 2x cube over x, that is 2x square plus 4y divided by x. And we recall the standard form of linear differential equation, dy by dx plus px into y equal to rx. So to convert in this form, we have to take this term on left hand side. Therefore dy by dx minus 4y over x equal to 2x square. So now we can compare this equation with this standard form, and we find that it is linear with y as dependent variable. Value of px is minus 4 by x and rx is 2x square. So this is now linear, which is linear with px, that is coefficient of y, which is minus 4 by x, and right hand side is 2x square. So right hand side we consider as rx. Now next step is we find out integrating factor. It is e to the power integral of px with respect to x. What is px? Px is minus 4 by x. So we integrate minus 4 by x with respect to x. And here minus 4 is constant. Integral of 1 by x is logarithmic function of x, and this we can rewrite as ln x raised to minus 4, and integrating factor turns out to be x raised to minus 4. So therefore integrating factor is x raised to minus 4. And we have ready-made formula for the general solution of linear differential equation of given differential equation is dependent variable is y times integrating factor equal to right hand side times integrating factor. Integration is with respect to x plus c. Integrating factor is x raised to minus 4. Rx, that is right hand side, is 2x square, and integrating factor is x raised to minus 4. Integral is with respect to x. So this we can rewrite as 2 times x raised to 2 minus 4, which is minus 2 dx. Parallel we can rewrite y times x raised to minus 4 as y over x raised to 4. Therefore y over x raised to 4 equal to 2 times integral is x to the power minus 2 plus 1, which is minus 1, divided by minus 1 plus c. Therefore y over x raised to 4 equal to minus 2 over x plus c. So this is the general solution. If we wish, we can multiply whole equation by x raised to 4 and we can rewrite our solution as in this form. Okay, by multiplying this equation by x raised to 4, here x raised to 4 will cancel out. Here we will have minus 2 x raised to 4 over x, that is x cube, plus c times x raised to 4. So this is the general solution of given differential equation, which was linear with y as dependent variable, where c is arbitrary constant. So this is all about this lecture. We have discussed all the three types of differential equations, but mainly you remember, first try to check whether your equation is separable or not. If it is not separable, then you can check whether it is exact or linear. So that is your choice. First, if you observe that your equation is linear, then directly try to solve it using the method of solving linear differential equation. If you feel that it is exact, then directly go for the method of solving exact differential equation. And if you don't find any of these three types, then we have discussed different categories of differential equations which can be converted into separable or into exact or linear differential equations. So this is all about today's session. I hope you like it. Thank you very much.